We're going to continue solving systems with substitution. Remember the equations that we have here, we have more quadratic equations. So notice a quadratic, 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 quadratic. Using substitution, remember we're going to take our expression and we're going to substitute it into the other equation. Since the x plus 4 is equal to y, I'm going to take the x plus 4 and substitute it in for y. That gives me x plus 4 equals x squared plus 8x plus 14. If you remember last time, in order to solve a quadratic equation, we set it equal to 0. So I'm going to subtract the x and subtract the 4. I get 0 equals x squared plus 7x plus 10. I'm looking for two numbers that multiply together, give me 10, add up to 7. And I have 2 and 5. That gives me x plus 2, x plus 5. So I have two answers, x equals -2 and -5. Now, if you remember, we have to write two ordered pairs. The first one is -2 and some number, and the second one is -5 and some number. What I like to do is pick the easier equation to plug it into. So if I'm plugging in -2, the top equation to me looks a little bit easier. So I'm going to take the -2 and plug it in. When I plug it in, what I have is -2 plus 4, which of course is 2. Now I'm going to take the -5 and I'm going to do the same thing. I'm going to plug it in. -5 plus 4 is -1. So those are my two ordered pairs. Now, looking at letter E, I'm going to take my expression right here and I'm going to substitute it into the other equation. Since this is equal to y, I'm plugging it in for y. I get x squared plus x minus 1 equals x squared minus x minus 9. Now, if we're looking closely, what we notice is that the x squareds cancel. We no longer have a quadratic equation, we have a linear equation. With a linear equation, we want to get the x's on one side. So I'm going to add the x, and I get 2x minus 1 equals -9. Add the 1, and I get 2x is equal to -8. I divide it by 2, x is equal to -4. Remember, our goal is to get an ordered pair. So the ordered pair is -4 and some number. So what I'm going to do is I'm going to take the -4 and I'm going to plug it into one of my equations. To me, the top one looks a little bit easier. So I'm going to plug it into each of those x's. Y equals -4 squared plus -4 minus 1. -4 squared is 16 minus 4 minus 1. 16 minus 4 is 12, minus 1 is 11. So that right there gives me my ordered pair, -4, 11. Now, for my last example, once again, process is the same. I'm going to take my expression. I'm going to substitute it into the other equation. So I get -x squared plus x plus 1 equals 2x squared plus 11x plus 4. X squareds can't cancel, so I still have a quadratic equation. That means I need to set it equal to 0. So I'm adding the x squared, subtracting the x, subtracting the 1, adding the x squared, subtracting the x, subtracting the 1. Here it is equal to 0. This right here gives me 3x squared plus 10x plus 3. I'm looking for two numbers that multiply together and give me 9 and add up to 10. That would be 9 and 1. Remember, because we have a leading coefficient of 3, I'm dividing each of these by 3. So I have 0 equals 9 divided by 3 is 3. And the other one is 3x plus 1. The bottom goes to the top. So that gives me two answers. One is -3. The other one is -1/3. So that means I'm going to write two ordered pairs, -3, comma, some number, and I have -1/3 and some number. Starting with the -3 because it's a little bit easier, I'm going to pick one of the equations. In my mind, the top one looks a little bit easier. So when I plug it in, I get y is equal to -3 squared plus -3 plus 1. -3 squared is 9, but there's a negative, so -9 minus 3 plus 1. -9 minus 3 is -12, plus 1 is -11. Now, if I take my 1/3 and I plug it in to that same equation, what I get is -1/3 and then -1/3. -1/3 squared. 1 squared is 1. 3 squared is 9. So that would be -1/9. Here I have a -1/3. And I have a plus 1. I need a common denominator, which of course would be 9. So -1/9. That stays the same. This is -3/9. And this right here would be 9/9. -4 plus 9 is 5. So I get 5/9. And these are my two ordered pairs.